one layer up from a lot of us in the sense of towards proof assistant. So he has done the type theory and the proof theory. He has worked on the Matita project in Bologna, which was a team implementation of a theorem prover for the calculus of industry construction. And then he has put this expertise to good use by being one of the main developers of the Coq system. Notably, he worked on the SS Reflect set of tactics and also the mathematical libraries around it, which is the tactic language of choice for people doing formalized mathematics in Coq instead of formalized programming language research, for example. And he's going to tell us about a more recent experiment of this.
Okay, thank you. First of all, I'd like to thank the program committee. I feel I'm new to this community. This is my first ML workshop, my first ICFP. As Gabriel said, I work in an area that is not so far away, but it's not exactly the one of programming languages. And it was a nice request to be invited. So, I've never contributed to ML or its theory nor its implementation, but I've been for a long time a user. Since my master, it was 15 years ago, I got interested in these tools, these interactive provers, and I've been programming. I really like to program. I've been programming these tools for 15 years now. And now that I'm in France, well, I don't work on Matita anymore. I work on Coq. And that's roughly the architecture of the system. There is a component that is in charge, the kernel that is in charge of checking the correctness of proofs. And this is the part to really trust in, the one that certifies the procedure in Coq. And then on top of that, there is an elaborator that is in charge of giving sense to the expressions written by the user. So you should think of it as a sort of fancy type inference. On top of that, you develop your commands, your tactics. What is most interesting to me, and actually one of the reasons why Coq was successful, is that users managed to deploy Coq in different areas, doing different things. And this is thanks to the user extensions. People developed, we saw Robert giving a talk at ICFP, a sort of framework for separation logics by doing fancy things at the tactic level, or the formalization about mathematics Gabriel was talking about. Well, the fact that you could extend the elaborator was crucial, because when you write a mathematical formula, there is a lot of implicit content you are going, and you expect an informed reader to understand a lot of things. And extending the elaborator was a way to make Coq an informed reader. And so, programming language-wise, how are things? So Coq is written in OCaml, and the user extensions are written in specific constrained languages that really have a Prolog-ish flavor. I'm talking about here for the laboratory, it would be the language of canonical structures that extend unification rules, with rules, or the type classes mechanism you may be familiar with from other programming languages, and or the ELPI language that, at least in its core, really looks like a logic programming language. So far so good. What's the problem? What's the motivation of my research? Well, if we look at the quality, well, when you are a developer, you open the box, so you know what is nice and what is not. And I have to say that the kernel is pretty decent. We don't find many bugs in there. It's mostly a purely functional piece of code. We use mutability a little for performances, but I'm pretty happy about it. This is much uglier as a elaborator, and as a consequence, everything you build on top of it is even worse. And so at some point, I wanted to improve the user experience here in the user extensions by, for example, trying to do some bit of static analysis of their extensions. And it turned out that they use this box as a black box, so if you try to, that is not well specified, so if you try to understand what these extensions do, it's hard without having this component that is so crucial, that is full of bugs and not very well specified. So why? Why is it so bad? Well, here everything is decidable. Lambdas come with a type for the bound variable. And polymorphism is like system F, so you have the polymorphic function and then the type to which it is instantiated. here, well, the calculus is the same, but you want to give the feeling to the user that they are using ML, not system F, for example. So you don't annotate the binders. You omit the types of polymorphic function instantiations. And inferring a type in Coq is complicated because types can contain values. And the terms of Coq, the values of Coq, can be used to represent proofs. So it's immediately crystal clear that inferring a type can be, at least in theory, as hard as doing proof search. Okay? So there are reasons why the algorithms that are here are tricky. Also, and this is where the research comes in, I think that the programming language that we use to write these components is not very appropriate. What makes the algorithm even more trickier is that you have to deal with binders that are encoded as integers, the brown indices. So you have to lift and shift things. And then you're implementing unification, and there is no support for unification variables in ML. You encode them as numbers plus an environment in which you attach to them types and eventually an assignment that you have to trade, a substitution that you have to pass around and never forget. Some of the algorithms for type inference are better expressed in terms of constraints, and ML gives you no support for that. So you start working with a working list that you pull around, and then sometimes you take problems out of the working list, sometimes you forget. So it makes things trickier. So the plan was to come up with a language that is nice to write the user extensions, but that is also can also be used to at least replace partially the components that I'm not very happy about. And that's the subject of the talk of today. This language is called ELPI. It is an extension language. So it comes as a library that you link in a larger application. And it comes with API and FFI so that you can write glue code that exposes some of the state of your bigger application to the programming language. And also maybe the syntax with quotation and stuff that we will see in a short demo. And this language is very high level to me. For example, it gives you native support for binders, for unification variables, and you can do a bit of constraint programming also. So it seems like a decent framework to express the elaborator component and the upper layers. It's free software, developed by myself and Claudio, and the easiest way to define it is to say that it's a mixture of lambda prolog and constraint handling rules, and I will show you how they are mixed in this language. So the outline of the talk, I have to present you the language. So first the lambda prolog fragment, and then I will add constraints. Then I didn't want to show you exactly how I integrated with Coq because it's too complicated for a short talk. Take a week, I guess. So I came up with a sort of toy ML programming language. I wrote an ML part of it in ML. The language features left polymorphism and the quality types. But instead of writing the type check and the type inference algorithm in ML, I linked ELPI and I wrote it in ELPI. Okay, and this will be the meat of the talk. I will also want to show just a quantitative demo, let's say, of what I did in Coq so far with this language. And finally, in time permitting, I will spend a few words on the implementation of it itself. So, lambda prolog. Let's say the hello world program in lambda prolog is a type checker for simply type lambda calculus. So on the left you have the syntax, and on the right you have how the terms are represented in lambda prolog. It uses an higher order abstract syntax approach, so you use the binders of lambda prolog to represent the binders of your object language. You don't have anything here for variables because you will reuse the variables, the bound variables of lambda prolog. For application, it's just a node with two terms. And for lambdas, you can see you take a function, so it is a way to abstract a term over another. And of course, you have the combinator for types, and you also have variables that we will reuse the one of lambda prolog. And that's the syntax of lambda prolog. I'm not a big fan of it, but I couldn't find a better one, so here it is. This is the identity function, so you have the lambda node, and then the identity function of lambda prolog. This reads lambda x, and you don't need to put the parentheses. For example, the k combinator can be written like that, lambda x, lambda y, x. Okay? Now, what about the typing rules? So up there is the declaration of the of predicate. It's a predicate, but I won't give you relational or declarative reading of my programs, I will give you an operational one, which is the one in the term. So there is a way to compute, to associate to a term a type. And there are also annotations, input and output. They play no role in this example, but will play a role afterwards. Programs are organized in clauses exactly as our type system are organized in rules. The convention is that capital letters are variable. So every time you use this rule, they are fresh. And they read like that. So to check an application of a head to an argument, well, we first have checked the head. This type must be an arrow from S to T. And the argument must be type S, so that it fits here. And what you obtain is the type of the entire application. This is more interesting. To type check a lambda, where F is a lambda Prolog function grabbing for the body of the lambda, well, the type would be an arrow from S to T. And how do I type check it? Well, first of all, let's introduce in my program a fresh constant. Okay. Then add to my program a clause about this fresh constant that says that it has type S, like adding an extra rule here. And finally, let's apply the function to this fresh constant, obtaining the body, where all the occurrences of the bound variable are replaced by the constant, and check it recursively. I will use a subscript for variables when they are not quantified. Here, every time I use these rules, these variables are new. But when I put subscript 1, 2, 3, they are pre-existing. Okay. So let's try to type check lambda x, lambda y, x applies to y. We want our query, the question is which is the type Q, and this is our initial goal. So there is the term, and then a variable, and at the end of the program, here the variable will be assigned to some values, some type of expression that will be the result. So the first rule that applies here is the second one. And what really is happening is that the head of the clause, so what precedes the entail symbol, is unified with the goal. So if you align the two terms, F, your F would be unified with that part, oops, and while Q has to be unified with that part. Okay. So what happens when we apply the rule is that, well, we introduce a fresh constant in our program, C1. We also add to the program a clause that says that C1 is like H1. And we recursively go on F applied to X. F was bound to this expression, F applied to C, our fresh constant. So the new goal includes a beta radix there. Okay, C1. And if we fire the beta radix, we obtain the body of the function where X has been replaced by C1. And we also see that Q, our initial variable, has been assigned to a partial solution of our problem. It says, well, the type of your initial expression is an arrow, okay, from S1 to T1, and they will be synthesized later. Now, the same rule applies again. So we have a C2 with its type in the program. Again, the beta radix is there. And now, sorry, I think I should do this slow motion. Here we have T1. That was also there. So now here we have the arrow. Okay? Here we have the same beta radix as before. We reduced it. Now we are at the very body after the two abstractions. The first rule kicks in. So we have two things to do. Check the head and hope it has type arrow, and then check the argument. For the head, we have exactly this rule in our program. And it applies. What it does, it applies, but S1 has to be unified with arrow S32. S1 also appears here in our answer. So the first goal is solved and give us some information here. It's almost the type we expect for our query. It's just that it doesn't know that the input of this function matches the type of this argument here. And this is what happens when we solve the last goal that says that C2 has type S3, while in our program we know that it has type S2. So this imposes that S2 and S3 are the same. So this is our result, and that's how you could write it in the syntax we are familiar with. So how do we add constraints to that? Well, so far we had clauses manipulating goals, solving one goal, replacing one goal with many or with another goal. now we have this sort of special built-in that suspends, that generates what I call a constraint. Constraints are of the same nature of goals, and when they are put into the constraint store, they are labeled with a unification variable. In this case, then later on in the program, this unification variable may be assigned by unification. And in this case, the constraint is resumed. So C is moved back to the goals. This is one option. Another option is that a constraint handling rule kicks in. This rule reads, if the constraint store contains C and D, and the condition T holds, then remove D from the constraint store and toss it away, and put back G into the goals.
So what do the constraints correspond to in terms of your previous example?
There are no constraints in my previous example. In the next one, there will be. And so if you forget these quotes that they put around constraints, this looks pretty much like a regular constraint logic programming framework. But actually, the constraints are quoted. Okay? They are syntactified. And the rules, the CHR rules, work on the syntax. So this part of the language also works as a meta level. Okay? It can really see the syntax of the goals, and as you can see more goals than one. While Prolog sees one. You backchain on one goal and the others are there in a working list. Okay? But here you have a more global view on what's going on in your goal. And also you can access the full syntax of your goals. So a simple program, I have the data type of natural number with 0 as successor and 3 predicates, odd, even, and double. They are all flagged as input. Okay? What does it mean? It means that we use matching rather than unification. Or in another way, if I have a goal that is even of a variable x, logic programming would say, oh, even 0 is there, so a possible solution is that your x is 0. Okay? Or there is another solution. Maybe you could apply this rule and then that rule, so maybe your x is 2. We don't want to do that in this case. When odd is applied to a variable, we don't want to use these rules that I hope you can read and agree with me. We suspend. Okay? Whenever odd is applied to a variable, we create a new constraint that is exactly the goal we are handling with. So we suspend the goal. The same for even. Double, well, when there's a 0, there's a 0. When there is one successor, it puts 2 successors, so it's computed in double. And if the first argument is a variable, then we suspend again. And then there are 2 rules that govern constraints. If we find on the same variable that both even and odd, there's something wrong. The number cannot be both even and odd. So we put back to our goal state. And if we find out that something is supposed to be the double of something else, we put back some knowledge that that something must be an even number.
So the idea is that if I call it even with a constructor, one of the first rules will fire. And if I call it with a variable, the constraint rule will fire. But how do you know that?
No, wait. If I call it with a variable, they won't fire. This will fire, so it will be suspended and go to the constraint store. Then the semantics of the language is that as soon as you add something to the constraint store, you fire this rewriting system.
But how do you know that if you apply it to a variable, the first set of rules will not fire?
This is because we flagged the argument of odd not only as a natural number, but as an input. And in this case, this is the meaning. You're saying match on this, not try to generate, synthesize this. This is your input. It's not something else. So if you don't have input, do something else. Stop. So the program I want to run says that x is even, that the predecessor of x is not the double of something else. So we hope you agree with the meaning of what's written up there. Let's see how it succeeds. So first, even x, we said that should go here and be suspended. It is suspended and it is reified. The reification is very soft in the sense that the only thing we change is that the unification variables are frozen. They are replaced by constants. Then later in the program, x gets assigned to the successor of y. So we resume our suspended constraint. Now we have even successor of y. Now the regular, this rule fires. Okay. So we are with odd of y. Then out of y suspense, because y is not there. Now, negation in logic programming means try what's inside. If it succeeds, fail. If it fails, forget everything and succeed. And so we have to remember that we are doing a negation, and we start to process what's inside. What's inside is a double of variable, so it is suspended again. Now the second rule kicks in and puts back the fact that y must be even. Even y, again, is on a flexible term, so it's suspended, it goes back to our store. Now the first rule kicks in, because we have odd of y and even of y, so we put back fail. Not fail fails, so not fail succeeds, and we forget everything we did inside the negation. So this is the final state of the program: success, no more goals, and some constraint on y. Y is on. Okay. Questions on this weird language? So, from a more semantic point of view, lambda Prolog is typically explained as doing backward search. Okay? Each execution is finding a proof. You're building a proof tree. Now, with the fact that you can suspend certain goals, it means that you're not building your tree in a depth-first fashion. You can start on a branch and then stop and start with another branch. While the rules here are a bit of forward reasoning. So you go that way, and then you discover that these two branches, even if you didn't finish the proof, are maybe incompatible. Or maybe one implies the other. So you do a cut, and you close one of the branches, and you go to the premise of the cut with a theorem that you prove. From a programming perspective, that is the one I understand best, is that the first language is good for programming by recursion on syntax trees with binders, while the second one gives you a way to manipulate unification variables, as we will see better in another example. But it gives you first access to unification variables, and it lets you manage metadata on them. So the constraint store saying that x was an odd number to me is a metadata. It could be a bit of information on this variable. Now, the meat. Let's try this TOEML language. So I add a Latin and an equality test. I add some type constructors, pairs, lists, etc. Variables, of course. And these are for monomorphic type. For type schemas, I have quantifications, and I have two of them. In standard ML, this would be tick alpha, and this would be double tick alpha. These are quantification over types that are required to be equality types, types for which I know a comparison function. Okay. So the rules, application and lambdas are the same. I just put this boring data all around. For the variables, well, when I pull something from the context, it might be a type schema that I have to specialize to the monomorphic type tau and give it to the variable. For the Latin is the usual rule. I give a monomorphic type to the expression, and then before putting the variable in the context, I try to, I make a type schema out of it, looking at what is in gamma. And for the quality test, I then check the two expressions that will be of the same type, and such a type must be an equality type. Okay? So let's define the other things. So how do I generate a type schema? This also explains what this data is about. Well, of course, you get the free variables in tau, the free variables in the context, you make the difference, and then you obtain the set of variables you want to abstract. But then, if the variable is in theta, then you make a quantification constraint to be an equality type, otherwise we don't. Okay. So theta keeps track of the variables that talk about equality types. And for instantiation, well, a monomorphic type specializes with itself. A regular quantification, well, you can just pick the monomorphic type you want. But when the quantification is the constrained one, the type you choose must be an equality type. And equality type, Booleans and integers are equality types. List of tau is if tau is, and for pairs is the rule you imagine. And for variables, well, they are if they are in theta. Okay? So I don't pretend to be formal in that, it's just to give you an idea of this algorithm. There are some details hidden there. And the only point I want to make is that this is pretty much syntax directed. I didn't tell you how to synthesize data, so if you take data as the full set, then you are not as general, okay? But okay, it gives you an idea of how the algorithm could go. So let's show the code. Okay. So let's go there. The most civilized way to implement. Can you read it from the back?
No.
No? This. A bit better. So, what was I saying? The most civilized way to write such an algorithm would be to map a syntax tree into a richer syntax tree where you have space for more information. Okay? For example, you may want to know the types of the subterms. Okay? But this would require me to write many syntax trees, and I was too lazy to do that. So I put in a hack that says, in the input syntax tree, I leave some holes that you will fill in with the type information I want. Okay? This saves me some code. And also, one would probably want to put in the input syntax tree locations of the terms in the text file so that it can report errors where they are. And again, I will put a trick on the mail side, remembering where terms were without polluting the syntax there. But it's not the most civilized way, but it's the most compact. And I think that for a demo is better this way. So, I guess here I made literal values that are not even there, but otherwise it's hard to make examples that are for integers. Then I have another node for global functions so that I can begin with a context with already some objects to play with. And then, of course, I have the application and the Lambda node, as we expect. And in the let binder, I left the space for the type of the bound expression so that I can see which are the type schemas that are inferred by this algorithm and print them to you. And then, of course, I have the node for the quality test. Then I need a bit of syntax for the types. Types can be either a monomorphic one that takes a type expression or a quantification. And the quantification here as a flag, it can be any variable or an equality type one. And type expressions are, as you expect, the or list pair, and the other type constructor we saw. So just to give an example, the main predicate in my program is called W, and for the global constants of the literal, it says that, well, literals are integers, plus is monomorphic type int. Okay, then let's see the nil constructor of list. It says for all x, list of x. This is how you would write a type schema. The type for cons size are the one you expect. The type for undup is a bit more interesting because undup is supposed to remove the list from a list, so it must be able to compare the elements of the list. And in this case, you see that the quantification here is constrained to quantify over equality terms. Okay. And well, I also have the pair constructor. Then application and lambda are the very same rule we saw before. It's just that you have mono all around the place. Because here I have the two categories. And for let, this is the place that we have to fill. We type check the expression and we give it to it a monomorphic type. Then we have this gamma bar operator that will give us a type schema eventually. And then what we load in our program is not the monomorphic type, but the eventually more polymorphic one that our gamma bar will produce. And for the quality test, well, this type will be Boolean, of course. We type check the left and the right hand side, they must have the same type, and then we test that this is a type for which we have an equality, and I pass to it the left hand side is just there for error reporting, so that we can say this term is not a type that is an equality.
So what is the part in blue?
It's a comment that I will implement later on. Okay. So there is an extra rule that says, well, if I want to give, this is the specialization one, if I want to give a monomorphic type to something, and this something happens to have a type schema, I have to specialize it. And again, I pass to the specialized term for error reporting purposes. Then there is the last line that is about error reporting that says, if amend appear, it means that the type expected for this term is not the one it has, so let's compute the one it has, and then raise a type error. This type error is a built-in that we define in ML that stops the execution and will print X as type, but it is expected to have type as other variable. And this thing here is just to avoid looping. Maybe there's a term that has no type at all, so I don't want to have my error handler to produce an error and loop for it. It's just a detail. Okay, then let's look at specialization. If I have to specialize, remember F here. So this is a function, okay? So we can use lambda Prolog application to pass arguments to this function. And if you want to specialize a quantification with no constraint, what we do, we pass a fresh variable, a fresh unification variable that will be substituted in place of the bound. So we obtain a monomorphic type with the bound variables that are replaced by unification variables. If it is an equality type, then I do the same, but I also impose that the variable I put in there is an equality type. And of course, when I reach the mono node, I say, okay, monomorphic type specializes to itself. I also want to put an error message. In the case this phase, it means that this and this are not unifiable. So I say a type error, X as type tie. Typically, I would, if I was more quiet, I would probably write X as a type schema that instantiates to type that is not unified with the expected type. That is more precise. And this is the main entry point of my program. This is the term, this is the type of the entire expression. I start by saying theta of the empty list, and then I call my W. So what's theta? Theta is just for constraints, so it has only one clause. That the only thing it does, it puts a constraint in the constraint store. And the fact that here I put no unification variables, it means that it will never be resumed. It will just be a constraint living there. And then I have another rule that says, whenever someone puts in a new constraint that is EQ bar on a variable v, I will replace theta of L with theta v cons L whenever v is not already in theta. And this mem theta is just written like that because I said that unification variables are frozen when you generate a constraint. Okay, it's a sort of soft verification, and this means that you put the special UVAR node around them. This would be the constant, and this plays no role here would be the arguments. Unification variables in lambda Prolog are higher order, so they have arguments, and we are not using them because the unification we need here is really first order, so I ignore that part of the information attached to unification variables. EQ bar. EQ bar is pretty much as in the slide. I should have lost here. EQ bar is pretty much as in the slide, so bool integer is fine. List of A is an EQ bar is if A is an EQ bar, and so on and so forth. If I encounter a variable, then I generate an EQ bar constraints that will be recorded in data. Otherwise, I say a type error. This is why I passed X in the first place. And this is EQ type error, so it's another built-in I created that will print a different error message. Now, gamma bar. Gamma bar takes a monomorphic type and will produce a type schema. This time, I'm not really using the constraint handling rules as manipulating constraints, as I did with theta, for example. I just use it as a meta level. Okay? So whenever I generate a constraint called gamma bar with the monotype and the type schema associated with it, what I do here, I match in the constraint store, I find data so that I have the list of EQ type variables. This is the way how I can access, this is the gamma bar constraint that was created. And as you can see, there is a part I didn't talk about before, that is the context. So the hypothetical part of the program, the clauses that were added by implication. Okay, if we go here, this G is a list of things that have this shape or that shape. Okay? So So I have access to everything. And then I call a piece of code that will generalize my monomorphic type to polymorphic one, and then I put back the goal that says, well, this solution you were looking for from the meta level is that the type schema is this poly T. And well, the code of generalize is not very deep. You collect the free variables in the monomorphic type, the free variables in gamma, you make the subtraction, you obtain the set of variables you want to quantify, and then you quantify them. Of course, you are at the meta level, so you can see the syntax of your term, you can plug and play with your term as you like. The only interesting part here is that whenever I have to bind a variable x, I look inside theta. If it is there, here I'm generating this quantification. This is the flag that constrains or not the quantification, and if the variable happens to be in theta, I say qt, otherwise I say any. Then there is some very nice lambda Prolog code about copying terms that is folklore. I find it nice because it's the identity function, but you can make a lot of things with it, like changing just one case and saying this variable should be replaced by this one variable. But anyway, that's not the point of my talk. So let's try to execute so bigger. I prepare some examples that clearly work because I believe it's not too broken. It could have worked. So at the very beginning, the system prints the signature of the two built-in predicates that I defined. One is type error with the 3 arguments, and the other one is the quality type error with another. We will see in a minute how we define it. So the first example, we type check 3 equal 2. The system is happy and prints the type of the expression that is a monomorphic type Booleans. I try to compare 2 functions, and this is the monomorphic type Booleans. If we go back at the program, we see that even before checking a Q-bar, we say already that the expression has type monobool. Okay, so we can output something even if we are going to give an error. And the error is that there is an equality type constraint unsatisfied at this term, as we expect. Here I play a bit with polymorphism. I define the identity function, I apply it to a list. So the type I obtain is a monomorphic one. It's a list of something. We don't know what is something. What is this something yet? It's a unification value. We got the type, and the type inferred for ID is alpha row alpha for all alpha unconstrained. Data type. This is just to check that I know how to specialize the type schemas. So I apply the identity to a list and to an integer. I get the pair of list and integer, and the type is still the one we expect. This time I define the reflexivity function that is completely useless. It tests if the input is equal to itself, and then I apply it to a list. Well, the output is a Boolean because equal is of type bool produces a Boolean, and the type that was inferred for this stupid reflexivity function is alpha bool, where the alpha is constrained to be an EQ type, so double tick alpha. And of course, if I apply this reflexivity function to a function, I get an equality type constraint favor here because the arrow type is not an equality type. Then this is a more interesting example. Unda removes duplicates, so we saw that it was expected that it's a type schema, but it is constrained. And then I compute the size, and this gives me the cardinality of a list, as a set. And of course, the type we obtain is integer, but the type we obtain for cardinality is constrained over a Q type. Okay. This means that the constraint that comes from here has been inherited to there. So it seems it works. And this is a more convoluted example that just checks that this inner let here that uses a variable bound here, x, but a bound variable y there, is not generalized too much. Indeed, the type of G is alpha, or the pair of alpha is something else. Alpha is quantified, but the something else is not. So it's just to check that I was really traversing the context and see what's in there. And then a couple of errors. Size 1, there's an error. It's type integer, but is expected to be a list of something. And this other one is more interesting. I'm comparing a list with a pair, and the type error I get is a bit bizarre. It is not the one I expect. It is not the one Kaveh would give me, as far as I remember. That says that the constructor of the pair data type has type whatever pair, but I expect something that has type something else list. And this is because, even if I didn't tell you explicitly, the type inference algorithm we wrote is bidirectional. Here we are type checking the left-hand side of the quality of the quality test, and while we type check the right-hand side, we already know the type T that was inferred from the left-hand side. And if we go to the application, it means that this T is known. So when we type check the head, we check immediately that it can produce the type we expect, even before checking the arguments. If we want to make it monodirectional, that's the question of Gabriel, if I manage to edit my buffer, I could do it like that. So I type check the right-hand side, giving no expected type, and then I compare the two types, and if they differ, then I give an error. And in this case, you will get the familiar error message that says this expression is type pair of integer, but it should be a list. Sure?
You haven't recompiled anything, you just rerun the example and it changed.
It's an interpreter. I saved the
So the ToyML program executes this code at some time.
Yes, because it is an interpreter. So you just change the source and you do this.
Magic.
Not so magic. Anyway, so let's look at the ML side of things. How much time do I have? I guess I should speed up. So this is the actual syntax tree the parser could give me. And as you see, for each node, I also have the position in the source text. And it's really raw syntax tree, because here for constant I didn't do the lexical analysis yet. I don't know if it is bound by this thing, for example, or if it is a global one. So we'll do it on the fly later on. This is the syntax tree, and this is the code you have to write. So these are the two hacks I pulled. One to inject into my input some questions, and this is to save the position of all the terms I generate so that I can map them back to the original location. And here I'm using a feature of ELPI that lets you extend the state that is used by the compiler, and this is very useful if you add quotations, as we will see later. And so I add to it a field that I use to map back things to positions in the source text. That's not very deep, that's what it does. Then I have to build a function that embeds the terms, the ML terms, into the ELPI world. These are the names of the nodes in ELPI, and this is the boring code that does it. For example, for the application, there's nothing, just but calling embed on the subterms, and then generate an application where the application node in head, then the head and the argument. For the lambda is a bit more interesting because you also have to use the lambda abstraction of lambda Prolog there, and I'm also passing around a context, so I put in the context the name of the bound variable so that when I encounter this node S, I know if S is in the context or not. In one case I make it global, in this case here I make it global and I translate the string. In this case I have to generate at the ground level, this is how it works, so I have to measure the size of the rest of the list. It's the distance from the root to the fifth. Anyway, you have to do the mapping. That's not rocket science, this mapping per se. It's quite boring. I'm pretty sure that one could write a PPX to generate it. Then I have two exceptions, and this is the way how I register built-ins in ELPI. I'm sorry, I have a JDT in my API. That's a discussion between us. So here I have a JDT describing the type of the built-in predicate. It has 3 inputs, for example, and in this case I'm not very precise on which kind of data I put in there, but I could put something that represents a list of strings, and then the ML code down here will receive a list of strings. So all the boilerplate translated things can be hidden behind the type declaration as the JDT. I also put some comments and some layout information here so that it prints the thing we saw before, the signature of the built-in predicates. And these are really ugly built-ins because they just raise an exception that will escape the interpreter and terminate the execution. Typically, you want to generate some data that is readable from the interpreter. But for this data, that's enough. Some code to print errors. And finally, there is some boring code to initialize the interpreter with the built-ins we just declared, pass the program, compile it. And then finally, whenever we have text and the AST, what we do, we generate a query that is main applied to the AST that I obtained by embedding the ML AST into ELPI. And then I also make a question here for the type of the expression that is what was printed. Then a few more steps to generate the executable. And it can either succeed, and in this case I have an assignment with all the answer to my questions. Otherwise I get an error, I get a partial assignment, so what was discovered so far, and then I print the error. And that's pretty much about it. The point I wanted to make sure in the main code is that there is the way to write built-in predicate, the FFI is based on GADTs, and it works pretty well in my opinion. And the other one is that you have to write these embedding functions. They are boring, so there is hope to mechanize them. I didn't do that. So, before concluding and taking some questions, I wanted to show you a little demo of what I did in COG with this language. This is a COG. How many of you did proofs in COG? Oh, quite some. I hope you will like that. So, this is just, I'm loading ELPI as a plugin in COG. It's not released yet, but you can go to GitHub and play with it if you want. This is a Lambda Prolog program, and okay, it's a string, so I have to quote strings in the program. So there is also a way to write the program in external file, but for demos it's better to put them in the buffer so that you can easily read it. This program takes main is the main entry point. It takes a list of arguments. If it's empty, it says hello world, where cog.say is one of the built-ins I defined in cog. And the other, if you give it a string, then it generates a message that is hello of that string. So hello world, hello cog. Then I define a print command that takes a string, it locates it, roughly using the locate command of cog, so it finds out what term is behind the string, and then it prints it. If the term was an inductive type, then it asks the environment to get some info about the inductive type, in particular the list of constructors, and it prints it. If it is a constant, it asks the environment the body is constant, okay, and it prints it. So for NAT, it will print 0 and S, and these are built-in data types as int string is just the internal data type of cog for references. You can easily embed it into cog, usually describe it, how to embed it into Lambda Prolog. Lambda Prolog is not structured data. It doesn't know what to do with that. It can print it, it can unify it, and it can use your APIs for that. But it's not structured data. And like strings, it's the same thing. You have some APIs, but they have no inductive structure. And for plus, you have printed. Plus is a fixed point. This is a pretty printing hint. I will come back to it in a minute. It is recursive on the first argument. It has type NAT, arrow NAT, arrow NAT. This is the recursive code, the binder for the recursive code. It takes two inputs, two natural numbers. It pattern matches over the first one. If it is 0, it gives back the second one. Otherwise, we name the predecessor, and what we output is the successor of the application of the recursive code to the predecessor and the other one. Of course, writing terms this way.
What if you do a mistake in your string definition? Do you have a next error message?
Depends, not yet. If you make a type, if the program fails, you have to think about producing the right error message, as I did in the other demo. If there is a type error in your program, you can ask the system to check it. So, I don't know if I do that, let's do NP. that. Okay. Now I have to repair my screen. Okay. So writing terms this way is pretty boring. So there is a way to tell ELPI what a quotation is. And in this case, the text between these double brackets is parsed using coq parser. And then the actual syntax tree of coq is embedded back to ELPI. So if I print this term, what I get is the translation of this term into ELPI. And this is an anti-quotation. It says lambda Prolog, and then A is just a variable that is not assigned. So what you get here is the application of, well, this is the real name of the class, of the addition to the variable that is bound there, and this unknown A. And this lets you build term step by step. So here, for example, I give a value to A, and the same text as before gives me something that, as the second argument, as the IP successor. Okay? So there are ways to use the parser and of the host application to write your terms. Clearly, the parser of coq is much more powerful than the one with ELPI. And the other thing I wanted to talk about are these pretty printing hints. And there's something that you can do, like saying that all pretty printing hints are the same. It is the same thing I would do for locations. If I put in my terms location, I don't want them to interfere with the meaning of these terms. I would like comparison to ignore them. So there is data behind this backtick X and backtick Y. Coq can read it and it can use it to print back things as they were input by the user, but they play no role in the programming language above. So they are really like in the unit. And what did I do with that? Well, so far I worked on extending comments, and I wrote a sort of derived thing, ASCII style or PPX deriving style. And this is an example I like. I define a tree with a leaf, or the node is made of a list of subtrees. Okay? And this is a very simple data type in programming languages, but in coq, you know, it's a bit boring to work with because, well, first of all, what I'm able to generate, I'm able to generate a comparison function, okay, among the induction principle mapping and stuff that I don't want to talk about, and also a proof of correctness of this comparison function. Okay, you cannot. The only thing you have to remember is 3EQ, and if I print the thing, it says that my Boolean function applies to x and y, must return true if and only if x is equal to y. So it's really the specification of a comparison function. And if you know, this is the induction principle that Cox generates for you when you define the data type, and it is a bit silly because you have to prove that P holds for any T, you have to prove it for the leaf, and you have to prove it for the node of L, but you know nothing about L. You expect the induction principle to tell you that your subtree is the property, otherwise you're not going to go very far. And the induction principle I generate is slightly better, but for the bound names that are chosen in an ugly way, it says that you still have to prove P for the node of H, but you know something more about H. You know that this predicate holds, and this is the unary parametricity translation that essentially of the list type essentially says that P holds all the elements of the list. Okay? And how did it happen? I didn't write the code to generate the unary parametricity translation. A colleague of mine tried to port the ML plugin for coq that generates the parametricity translations for coq terms from a version of coq to another. After a week, he gave up. It was too complicated for him because the API changed and it was a bit painful to do the translation. So he came to my office and said, explain me your thing, and then we tried to write the parametricity translation in your language. And 1 week after, he came back with the code that works. And so I was very happy. It means that the system is not just usable by me. And the other thing is that if the bricks are easy to write, like this one, and you have many at your disposal, and you can easily reuse them when you derive other stuff. So here, if I didn't have already in my toolkit a way to generate this kind of predicates, without the unary parametric translation, I would have needed more work. But it's so easy to write it down that a colleague wrote it for me. So, to conclude, I'm a bit late. This we saw it. A key ingredient of it is mutability of ML. In this way, you can get the garbage collector of your extension language pretty much aligned with the one of the kernel. So you don't provide the garbage collector and you get an efficient one. But I don't have time to give the details, and that's my conclusion. Thank you.
So do we have some questions? I asked some silly questions during the talk to train the audience to ask more questions. So, yes.
It's not really related to ELPI, but to your last example. So I guess you know that Ambrose Capote made some generic generation of inductive principle from variability. So have you defined you're showing the example on tree, but does it work on any inductive type within this system score? Do you work on the general framework or just some example?
I'll tell you in a minute. So this is the way I generate the things, and depending on the box, they either work on everything, like this one works for everything, or they have some limitation. For example, the quality test works for inductive type with indexes, when you can compare the index, for example, but this is the contextual reasoning, and this one doesn't, for example. I mean, I have ideas on how to do that, but it's not done yet. So, that's pretty much my answer. The status of things is that some of the blocks, like parametricity, is complete because someone figured out the details. For the other ones, you can plug you can do it by hand and replace the automatic generation by something you write yourself. It doesn't cover everything. Also, there is another limitation I should talk about for CAG. I don't cover yet mutual inductive types.
Yeah?
The problem with logic programming is to control some cost model of the execution. You need to have some idea of the complexity. Is the CHR system a way to have some control of?
No. CHR is pretty slow in general. It's known to be very high level, but not particularly fast.
It's not about constant or about being fast or not, but just to know the complexity of, for instance, type inference in ML in practice under some hypothesis is linear, you know that. Can we make some reasoning on your logic program to check that it's being details?
I'm afraid not. And there are a lot of things hidden behind the scenes that I'm not so sure would make the analysis very interesting, because you're doing the logic programming language is based on higher order unification. We have bounds on that, but it doesn't mean that my code is really as smart as this bound. So I'm not so sure. Yeah, higher order unification in the fragment that the Miller pattern should be linear. I'm not so sure my code is better. Sometimes it's sporadic, I'm really sure. So I'm not so sure you can really make a faithful analysis on my programs.
So let's thank the speaker again.